All right, let's begin. So this is going to be a significant figures problem. Related to section 1.1, problem number 35 on page 26. So say if we have a container here. Here's our container that we'll draw. And first we throw in a rock. And then we throw in another rock. And then we want to know, well, what's the total mass? What's the total mass that's in the container? Okay, that's our question. Well, first we need to know what is the mass of the first object, which we label M1. Say we had weighed it out beforehand, and we measured it to 12.23 grams. Okay. Kilograms, we'll say. Very big rock, very big container. And then we have mass 2 for the second rock, M sub 2. And say that one's 11.375 kilograms. First question might be, why is this one seem to be more accurate than this one, right? We have to the thousandth place 0.001, right? Here we have to the hundredths place. Maybe we were using different scales and they came from different places. But if we want to know what the total mass is, then we're talking about taking M1, adding that to M2, and that gives us M total, right? We can represent this by a simple addition problem of taking 12.23 kilograms, adding that to 11.375 kilograms. So significant figure problems always begin as a basic question of arithmetic. We simply add down. So here would be a 0, right? So we can put a 0 there. 5, 7 plus 3, 0, carry 1, right? So now this is 2 plus 3 is 5, plus another 1 that we carried, so 6. Put my decimal place. And then 2 plus 1 is 3, 1 plus 1 is 2. And then I'll carry down my units here for kilograms to denote mass. Here's my answer, right? No, this answer has more accuracy or significant figures than the measurements will allow. I have one measurement here and another measurement here. One of these two will limit the amount of accuracy or precision, I should use the word precision, associated with our final answer here. We look back at our original measurements. The first one, we note has 2 decimal places to the right of the decimal. Our second mass has 3 decimal places to the right of the decimal. For the rules of addition for significant figures, we know that that's what matters. We care all about how many decimal places to the right of the decimal does our measurement have. This one has 2 to the tens and hundreds place, tens, thousand, or tens, hundreds, and then thousands where the 5 is at. That means that this guy right here will limit the precision of our sum, or of the addition of these two. It's limited. I'm sorry, excuse me, this one. This one's limited right there, right? Because we have a whole bunch of precision right here to the thousandths place, but here we have only to the hundredths place. So that means our answer here, our sum, can only go to the hundredths place. It can only go right there. If it can only go to the hundredths place, then we can't have this thousandths place, that 5 that's there. That would be too accurate. So we got to get rid of that one. But before we lose that place or that degree of precision, we can do our typical mathematical rounding. So when we round this guy to the appropriate number, 23.6, not 0, but because this is a 5 greater than or equal to 5, right, you round up, then this becomes a 1. So 23.61 kilograms, right? So we round up this 5, so the 0 becomes a 1, right, goes to the next. So our total mass that's inside our container here is represented by 23.61 kilograms. Because of the precision limitation associated with this measurement here, only to the hundredths place, so our answer can only be to the hundredths place. Now say if we wanted to convert this 23.61 kilograms into grams, how would we do that? All right, well, we start with our 23.61 kilograms. We're going to have to put a conversion factor here. Here's our conversion factor. Something's going to go in the top, something's going to go in the bottom. And then we put over on our far right side after the equal sign, we're going to put what units we want to end up in. Say if I'm going to be converting this from kilograms into grams. Kilograms into grams. So that means that I'm starting in kilograms. I'm going to end up in grams over here. There's my grams. Now, what does the conversion factor look like? Remember, the conversion factor is numerically equivalent to 1. What does that mean? Well, numerically equivalent to 1 would be like if I say I have 1 meter, that's the same as 100 centimeters. 100 centimeters is the same as 1 meter, so it's effectively 1 over 1. Even though you're seeing 1 over 100, it's not 1/100th. This is the same on top as the bottom. If in math, so this is approximately equal to, same idea as, well, if I have the same number on top, same value on top as I do on the bottom, which 1 meter in terms of the amount is the same as 100 centimeters, that's the same as saying I have same over same. Same over same is 1. Mathematically, that means that we're not actually transforming this value, we're just changing the units. All right, so in this same fashion here, we got to put this conversion factor in terms of grams and kilograms. What we're converting into always goes in the numerator, in the top of our conversion factor. What we're converting from always goes in the denominator. We do that because this denominator will cancel. We'll lose kilograms and all we'll be left with is grams. Right? Because just like over here, if we have 5 over 5, that cancels to just 1, right? It's like if we said 5 times 2 over 5 times 3, these 5s would cancel, and all we'd be left with is 2/3. Same idea. We have kilograms in the numerator, kilograms in the denominator. So if you have something that's in the same as the numerator and the denominator, then they cancel, right? Or they no longer affect the math. All right, in 1 kilogram, how many grams are there? This is what you have to know. You have to know that there's 1,000 grams in a kilogram. Kilo is 1,000, right? That's our prefix. So that means my answer here is 23.61 times 1,000 divided by 1. Well, divided by 1 is the same thing as just multiplying by 1,000. So I can take my 23.61 and move my decimal place 3 places to the right. So I'll end up with 2, 3, 6, 1, and 0. Put a comma here. 23,610 grams. Notice here what I did. Because I have 3 zeros, that means I can move it 1, 2, and then 3. If I moved a third time into a blank space, I just had a 0 there. So 23,610 grams. That's how many grams there are in 23.61 kilograms. All right, thank you.